today. Right, so we're going to build bridges. Right, you remember like that slogan, build bridges, not walls. So today we're going to build bridges. Two, how to move between the electric potential and the electric field. So you remember what we've been doing for the last 2 or 3 classes. We decided to simplify our life, and we were have been moving, right? We're still sort of in the process. We've been moving from the vector quantities to scalar quantities, right? In order to simplify our life. And as a result, we developed a new energy approach where kinetic energy in collaboration with potential energy under the roof of conservation of mechanical energy allows us to solve problems, right? Which I usually call like an energy approach, right? And now, so what? Wait, I need to bring slides forward. Okay, and so now what are we doing today? Yeah, as I said, we replaced in the recent past electric force with the electric potential energy, and then we replaced the electric field, which is again vector quantity, with the electric potential. Since electric field and the electric potential, they both describe exactly the same thing, that electrical aura which is created by any charge system. Of course, there must be a relationship between them, right? So we must be able to move, for example, from the electric field to the electric potential, or in the opposite direction. So we should be able to move from the electric potential to the electric field. Again, because since they describe exactly the same thing, there must be a relationship between them. So pretty much the whole class today we're going to spend or dedicate to finding, establishing these relationships, and of course practicing them. Right. Sort of typical situation for people who work, for example, with electrical systems. Let's say you have complicated distribution of charges, right? And very complicated. And let's say you want to find the net electric field at a certain point, or maybe you want to find the function how electric field changes with position, right? And if you try to integrate and find electric field directly from distribution of charges, it can be, from the mathematical point of view, it can be ridiculously complicated, right? Maybe it's even impossible to solve that problem using analytical functions, simple, okay, not simple, but calculus. But if we find these bridges, we can do this in an attempt to simplify life, right? So, for example, instead of finding net electric field, we can first find the net electric potential, for example, at the point in which you're interested in, point in question, right? So let's say first you find the electric potential, and then if you know the bridge how to move back to the electric field, you can use that bridge and find the electric field now from from the net electric potential. This approach kind of longer, because first you need to find the electric potential, different quantity, and then only then you can move to find the electric field. So it's kind of a longer procedure, but it can be easier. It can be solvable. Instead of trying to move directly to the electric field, you detour slightly, but it can be this process can be easier, right? So you see, we need to know these bridges. We need to know how to move back and forth between these two quantities, because in this case you can make your life easier, right? And actually you can solve problems. Otherwise it can be ridiculously complicated. They will never be able to get it done. Right? Okay, so now I hope I convince you that these bridges, these relationships are needed, and now let's start finding them. There will be some derivation, and it's not that complicated, so I'm going to just use slides. So first bridge. Again, my slides are not in front. Okay, now. So the first bridge. How can we get electric potential, scalar quantity, out of the electric field, vector quantity? So where should we start? You know what? We introduce electric potential from the electric potential energy, right? And we also know that electric field is connected to the electric force, right? And we also remember from the recent past that we moved, you remember how we moved from the electric force to the electric potential energy. We looked at work done by electric force. And again, since electric potential energy is connected to the electric potential and the electric field is connected to the electric force, so in order to find this bridge, we need to look again deeper. Again, we need to dive into the expression for the work done by the electric force. And then, if we dive deep enough, we should be able to reveal that relationship between these two quantities. So let's imagine some arbitrary situation and look at work done by the electric field, because both of these quantities feels like must be there. Okay, so now let's imagine this arbitrary situation. Some point charge, Q, right? Then let's assume that this charge moves or is moved from, for example, initial point to the final point, and along a completely arbitrary path. I emphasize on this word, completely arbitrary path. We're not specifying this path. Right now it's completely arbitrary, right? But between this initial and that final point. And of course, it must be, as charge moves, it must, this area is exposed to some electrical aura, right? Let's say we describe it using the electric field. So then, as I said, let's calculate work, because I feel like the relationship must be inside of that expression for the work. Okay, so let's calculate work done by the electric force, because again, this charge is going to interact with the electric field, and there must be electric force over there, right? And you remember, again, we used this formula already like twice in this semester. And I told you usually, let's recall physics 1, where you use this formula to introduce work done by some force. In this case, it's electric force. So it's an integral from the initial to the final point and over dot product, scalar product. In this case, electric force dotted with infinitesimally small displacement. Again, what is small displacement? Yeah, it's a small infinitesimal small displacement over here. I can show it. ds green. You see that green vector ds. Okay, so now look, and where are we going to get our electric field and electric potential? Electric field, obvious, right? Because electric force is directly connected to the electric field, QE, right? So, of course, electric field will appear on this side of the equation, on the right-hand side. Then work also connected to the negative change in the electric potential energy. We used it, I think, in a previous class or couple of classes ago. Again, I told you, recall physics 1, right? And if force is conservative, of course, work done by that conservative force is equal to the negative change in the electric potential energy, right? So, and since potential energy is connected to the electric potential, so that's how electric potential is going to appear on the left-hand side of this equation. Okay, so yeah, it looks like this expression for work should give us this relationship. So now let's replace first, instead of work, I'm going to use delta U, right? Instead of work, delta U. On the right-hand side will be exactly the same, but I move this minus, you see, this minus to the right-hand side of the equation. So that minus appears over here in front of this integral. Right. So now next, since we know electric force equals to charge times the electric field. Charge is a constant factor, right? Will be inside of the integral. Of course, we can take it outside of the integral. So we're going to get something like this minus q times integral of E dot ds. Now, the last step in this derivation. Again, you remember the definition of the electric potential, how we introduce it. It's the electric potential energy divided by the probe charge. In this case, basically, it's a probe charge. right? So that's how we introduce the electric potential as U divided by Q. So basically it means, look, if we take this charge from the right hand side and move it to the left hand side, we will get delta U over Q, and of course that will be delta V. And the derivation is almost done. Basically 2.5 steps. All right, so as a result, delta U over Q, as I told you, it's a delta V, delta U over Q will be delta V, and what is left on the right hand side will be minus this integral. Tada! Basically, that's the first bridge. Okay, let me open it up separately over there and frame it. So delta V, which is basically potential difference, right? Between which points? Our final point, okay, that final point, right? And the initial point, potential difference equals to negative value of that integral between the initial point and the final point of E dot ds. So this formula will be used, yeah, a lot, right? Even closer to the end of the semester, we will be still recalling from time to time. I remember, guys,
Professor.
when we establish the relationships between the electric field and the electric potential, right? And we will use it again. Again, I emphasize, it doesn't give us the value of the electric potential. It gives us the potential difference between the final and the initial point. So on the right hand side, yeah, we have the electric field, but on the left hand side, we have delta V. We need to realize it. And of course, the typical place for really unnecessary mistakes. Students forget about this minus. Students forget about this minus. Okay, now let me move to the next slide. It's basically I copy it and paste. Now, strictly speaking, this integral, it's a calculus 3. It's an integration over a line, or linear integration, right? A line integral. And you know, what do we usually do with this type of integrals in this semester, right? So yeah, usually those integrals looks kind of scary, right? Complicated, but we usually handle them, take care of them without actually diving into calculus 3, right? Using some high school knowledge and so on. So we're going to do something similar with this integral. It looks scary, but you will see that it's not that bad for our particular situations. So first of all, let's sort of make this situation simpler. All right, so let's adjust it slightly. So first of all, E dot ds. Let me open the, okay. First, let's write explicitly E dot ds dot product. It's a magnitude of E, magnitude of ds, and times cosine of angle between them. You remember, right? Definition of dot product. And now let me open the picture from the previous slide. I just copied it and pasted, right? So what do we have here? E times cosine theta. So first of all, theta is this angle. It's the correct angle between the electric field and ds. You remember how to find the correct angle? You need to position tails of both vectors at the same point. And the angle less than 180 degrees is going to be the correct angle. So you see, ds and E are, the tails of ds and E are at the same point. So that is the correct angle. So now, what is E times cosine theta? Basically, look, E times cosine theta, it will be component of this electric field along S direction, right? So E times cosine theta, right? You can easily imagine the right triangle, all right? And you will see that ES is just a component. You see small E sub S appears, right? So it's just a small component of the electric field along the direction of motion, direction of ds. Okay, let me write
Wait,
that as
Professor, I have a question
yeah,
about that. So, are you creating that angle based off your displacement vector and your electric field vector?
yes, because what we basically explicitly wrote what E dot ds mean, right? E dot product is basically, remember, A dot B. Let's say vector A dotted or scalar product with vector B. It's a magnitude of A, magnitude of B times cosine of angle between them. So basically, yeah, I just wrote explicitly dot product, scalar product. And of course,
Okay.
according to basically definition of the scalar product, that's how angle is found. So you just need to
Yeah.
position tails of both vectors at the same point, and that is the correct angle for the scalar product. Right. So now
Okay.
that E cosine theta, yeah, it's just a component of the electric field along the s direction. So as a result, I can make this integral look simpler, minus integral of Es. Basically now it's a component ds. Now, who remembers the graphical meaning of an integral? Most of you remembers that, right? If you plot integrand, okay, let me show it. Integrand is just a function, in this case e sub s. If you plot e sub s versus the variable of integration s, the area under that plot is the value of the integral. It's in my case, when I was in high school, that's we learned it in high school. In your case, I don't know. Probably some of you learned that in high school, some of you learned it in calculus, maybe at the university, right? So, as what I just said, if you plot E sub s along the vertical axis versus s, the variable of integration, and let's say you have this is the plot which shows the relationship between E sub s and s, and the value of this integral, equals to the area under this plot, again between the initial and the final point. That's the graphical meaning of an integral. It's just basically basics of calculus. And so now we're not going to take integrals. We're going to calculate areas. And usually this dependence is going to be linear. It's going to be either a straight horizontal line, or maybe a straight line up, or straight down, something simple. And every time we will have to just calculate area over a rectangular or over a triangle, something simple. But of course, if some of you are quite comfortable with integrals, you can integrate also, not a big deal. But guys, don't forget about the minus in front, because area is going to give us the value of the integral. Okay, let me open it up here. So area equals to that integral. But then, since at the end of the day we need to know delta V equals to minus that area. So find area, and don't forget to put minus in front. That's the most typical mistakes, especially at the very beginning, right? Students forget about, so they their brains remember, okay, it's connected to the area, right? So yeah, they diligently calculate area, but then they forget to add minus, right? And making silly mistakes, right? Right, so that's what we're going to do. And it's not the whole story. We're going to make situation even easier. So in all our problems, we're going to have one-dimensional situation. So pretty much instead of this arbitrary s direction, which can be this way, that way, basically arbitrary means any possible directions, right? But we're going to restrict ourselves to one-dimensional case along x-axis. So electric field is going to be one-dimensional vector. It's either, if it's positive, so it points along the positive x direction. If it's negative, negative x direction, right? So we're going to have only E sub x. And instead of s, of course, x. So we're going to see plots like E sub x versus x. There will be some curve, right? And we will be calculating area. So situation will be even easier, right? So so most of the time, instead of s, we're going to see x, and the integrals are going to look like this. Again, for those of you who are comfortable integrating, most of these integrals are going to be simple, right? Most of the time, we're going to just calculate areas. So that's what we need to know in order to move again from the electric field. And here we have change in the electric potential between the initial and the final point. Right? I think now it's time for me, of course, to start looking at examples. Let me check if I correct. Yeah. So what do we have here? It's an example. It's not a problem. It's example from the book 26.1. And I find it interesting, right? So what is given? Plot E sub x. As I just promised to you, in our problems, we're going to have one-dimensional situations, and the electric field is going to be only along the x-axis. Right. So E sub x. Okay, now you see we have now electric field, units of the electric field, volts per meters. It can be easily shown that newtons per coulombs, that's what we've been using up to this point, and volts per meter is basically the same. Right, you can easily play with those units, and you can show that newtons per coulombs and volts per meters, they're equal, right? They just juggle a little bit units. Then E sub x versus x. That's what is given, and you see the plot. It's just a straight line. And we also know that a value of the electric field at point x equals 1 meter. Here, meters. Again, guys, pay attention if plots are given. Pay attention which units are given, centimeters or millimeters or meters, because yeah, sometimes students in a rush, they don't look at the units, and as a result, of course, they use centimeters where meters are needed, and some unnecessary mistakes. Then, so what's the question? So basically, we have information about electric field, and we need to get information about the electric potential. So basically, we need to use the bridge which we just established, which we just built, right? So which give us the way of moving from the electric field to the electric potential. That's what we have situation. And we need to find how electric potential changes with x. So basically, we need to find the function, right? And additional piece of information is given. It is given so that at the origin, at x equals 0, the value of the electric potential is 0. Basically, they give us, okay, guys, move to the electric potential and use this reference point, or use this point as the reference point for the electric potential. Because you remember, you can position a reference point at any point you want, right? But in this case, they suggested, let's use this point as the reference point. So that's the problem. And before we start discussing the solution and started writing anything, okay, let me emphasize. So what's the direction of the electric field? Since you see E sub x are positive, it means that the electric field points in the positive x direction. If this graph, were under, this axis, x-axis, right? So E would be negative, and that would mean electric field points in the negative x direction. So positive values of the electric field, in this case, one-dimensional vector, it means positive x direction, negative values, negative x directions, right? Okay, so after discussing that, now let's actually start solving it. And again, since we need to use this bridge, which moves us from electric field to the electric potential, so we need to use what we just derived. Delta V equals to minus integral from x initial to x final of E. Okay, I'm not going to write E dot ds because now we have our simplest possible situation, one-dimensional. So it's a E sub x dx. So that's a general formula. Right, let me frame it. And now we need to use it. Right, it feels like, okay, I will try for a few extra minutes and then maybe I will have to change marker. So what do we have to do? Yeah, we need to apply this. But first of all, before we start applying it, we need to figure out which points can be used as initial point and which point can be used as the final point. Yeah, this formula is correct for any initial and the final point. Any, right? So no restrictions. So it's just based on what is given in the problem and what needs to be found, we have to make a decision. Which point can be used as the initial point, as an initial point, and which point can be used as the final point. Okay, let me do that. So first, initial point. Which point should be used as initial? Usually at this point, students can easily tell. Since we have some information about the electric potential at the origin, right, immediately. So it's a clear indication that this point should be used as our initial point. Okay, so let me write, let x equal 0 be our x initial. Then, about the final point. Which point should we take as our final point? Okay, at this place I will pause and think, guys, which point can be used, or should be used, not can be used, should be used as a final point. Usually during the normal semester when we're at school, usually I bug students, right? And so far, most of the time students pick, I don't want to say a wrong point. It's better to say not completely correct point. Okay, think for yourself, right? So which point would you pick? And then I will tell you the reasoning. Usually, most of the time, students tell me, we're going to pick point 2 as they pick point 2 as the final point. But in this case, okay, you know what? Let me check your chat because it looks like there is some activity you're trying probably to answer. X equals 1, seconded, yeah, that's, okay, thank you guys, right? So basically you confirm, right? So these are usually the options which students offer to use. But what if, for example, I follow your suggestion, and let's say I use x equals 1 as my final point, right? So look, this delta v, of course, I can write as v final minus v initial. V initial, it's v at x equals 0, it will be 0. And then on the left-hand side, what will be left? V at final point, v at 1. As a result, again, you see here we will have v at 0.1. As a result, when you calculate the value of this integral, what will you find? You will find the value of the electric potential at your point 1. But what's the question of the problem, in the problem? We need to find the function. We need to find the function how v changes with x, pretty much so we can use that function to find the value of v at any point. But when you use, for example, x equals 1 as your final point, you will find the value of the electric potential at that particular point only. But we need to know the function. We need to look globally. We need to generalize the situation. But you're trying to be very particular. Okay, I want to find just electric potential at point 1. It's not completely wrong, but you will find only a small piece of information which we want to find eventually. And the same story if you pick x equals 2 as your final point. Again, you will be able to find the value of the potential at that particular point only. But we want to find function. If the question were different, if the question was find the value of the electric potential at x equals 2, what you suggested would be absolutely correct. Just x equal 2 is the final point, and of course, using that formula, we can find the value of the potential at that point. But the question is more general. Find the function. So as a result, what you suggested, it's not completely wrong, but it's not completely correct, because we wouldn't be able to find function. Okay, so now as a result, the correct suggestion for the second point, for the final point, is an arbitrary x. Let me use green, for example. So this, let's say, x, completely arbitrary x. So let me write something like let arbitrary x be our x final. So that's the correct. We just need to pick a completely arbitrary x. And you could have drawn this, oh yeah, position this x, for example, here or there. It's completely arbitrary x. Pretty much x, which can be anywhere. Right. Okay, so that's what we need to pick. And so as a result, now, yeah, we can start writing explicitly this formula, this bridge for chosen points. Right. So now, all right, let me write, so delta v, which is v final point is at x, it's arbitrary x, right, final point, minus v at initial point, v at x equals 0 equals minus integral from 0 to x, e sub x dx. So now I wrote explicitly based on selected points. Right. Okay, so now, of course, you know what? I don't want to dump v at x equals 0 immediately. Right? Let me dump it in the next line. Because sometimes value of the electric potential is given at a certain point and it's not 0. So it means that you need to move this to the other side in order to involve into the calculations and so on and so forth, right? So let me, this will be the value of the integral between, the value of the area. So, of course, I can draw this line. I can label, for example, this is O, A, and this point. Okay, you know what? Let me write underneath. You will see in a second why. O, A, B. Right. Okay, so this will be negative area of this triangle OAB. Okay, even I can highlight it. Something like this. Right. So this equals to minus area over. Right. You know what? Let me write it on the next line. I cannot fit it, so let me rewrite this. V at x, that's our that's what we want to find, equals to, this goes to that side with plus, so it will be v at x equals to 0, and this minus area over triangle OAB. Okay, it's better. Right? And only now I will dump this because it's 0, but in general it doesn't have to be 0 all the time. Sometimes problem gives you that V at a certain point can be, minus 50 volts or 50 volts or 25 volts or something else, right? But in this case, yeah, this is 0. And we can dump it, right? And I don't like that these two almost zeros on top of each other. Okay. So now we just need to calculate area. V at x equals minus area, you remember what triangle, it's 1 over 2, times base, which is this distance, right? X, right? This distance equals to x. And then times height. So in order to find this height, of course, we need to write an equation which describes this function, this line, right? Without that equation, we cannot write this height. So what's the equation of this line? It's a straight line which goes through the origin. So that free term must be 0, right? Because it goes through the 0. And then we need to know the slope in order to write this function. So you remember, it should be this. This equals to slope, the value of the slope times x. The slope can be easily found, right, using this point x equals 1. Right? So at x equals 1, the value of the electric field is 1000. So the slope is 1000. So as a result, I can write my function this way. E sub x equals to 1000 times x. And the free term is 0 because the function goes to the origin. If this function was slightly higher, and of course we will have some positive value of that free term. If it was lower, then of course we'll have again non-zero free term. So that's the equation describing this plot. So as a result, this height will be what? At value at x equals x. So this will be, let me show this something like this. So this will be 1000 times x. So this height is 1000 times x, right? Okay, so we can now write that height over here. So it will be 1000 times x. Okay, this and that will be partially cancelled. We'll get minus 500 times x squared. So that's the answer. So that's v as a function of x. Let me write separately, minus 500 times x squared. Of course, I can frame it because that's the answer. And let me plot it. Right, so let's say I will plot it here. So this will be, let's say, v, of course, units of v. And let's say this is x in meters. And our points 1 and 2, let's say 1, 2, and our plot is it's a parabola with branches down. And of course, we only know about the electric field on the positive x-axis, right? So we don't know anything what happens here below x equals 0. So we cannot say anything about the electric potential on this side of the coordinate system. So we can only say about this. So it will be some kind of parabola like this. And at x equals 1, the value of the potential will be minus 500. Right. So that's the plot, and that is the function. But again, most of the time, the questions are about finding the electric potential at a particular point. Then another thing I want to emphasize, guys, if this information were not given, the value of potential at x equals 0 equals 0, we would be able to find what? If this information were not given, what would we be able to find? Only delta V. But with this additional piece of information, we can find actually the value of a potential, in this case at any point. But otherwise, we will be able to find only potential difference. Okay, so that's the example. It's a nice example. Right. And now I think I need to switch back to slides. There will be a question for you, and then we'll continue moving. Okay, all right, so this is the example which we just discussed, and now question for you. Again, the poll is in the chat, right? This time I created 3 polls, right? I think. So the first one, again, we have some information about the electric field. You see, E sub x, one-dimensional case, our case is basically. Again, in volts per meters. Okay, let's answer this question and then we'll have a break. And yeah, you see everything, right? So electric field goes down linearly, and then at x equals 1, it becomes 0 and stays 0, right? We don't know what happens outside of this range of x's. So can you find the value of the electric potential at point x equals 1 if we know that the electric potential is 0 at the origin? Again, we need to find the value of the potential at x equals 1, x equals 1, if we know that v at 0 is 0. And plenty of options, 5. Okay, give it a try. I will look, and then once you, okay, maybe I will discuss the solution after the break. So now you can answer it, and right, we'll have 10 minutes break, and then after the break I will discuss this. We need to start or continue. So question is, after what we discussed, the question is straightforward, right? First of all, of course, we need to make a decision which point is initial, which point is final. In this case, it's obvious. Since we have information about the electric potential at the origin, it's 0, right? So that will be our initial point, right? And the final point, of course, will be x equals 1 in this case, because we need to find the value of the electric potential at that point, right? So obviously, in this case, point x equal 1 is our final point, right? And so now we just need to calculate area, right? So v sub initial is 0 because it's given. This is our answer. And so in order to get this answer, of course, we need to calculate area of the of this triangle, because that's the area under the plot. And don't forget about the minus, because again, most of the time students forget about this minus, but this time I see you remember that, because usually during the normal semesters it's sort of like a 50-50, right? Some students usually pick 1000 volts, and the rest, like 50%, pick minus 1000 volts, right? So in this case, area, of course, it's area of a triangle. It's 1/2. Height is 2000, right? And base is 1 meters. So of course you're getting 1000, but again, as I told you, some students forget about the minus, and usually 50-50. 50% picks students picks B answer, and 50% of students pick minus 1000. But in this case, yeah, most of you pick the correct answer, D, minus 1000 volts. So that's the value of the electric potential at that point. Okay, great. So now next bridge in the opposite direction. So now, of course, how can we get the electric field out of the electric potential? So now we want to get vector quantity out of a scalar quantity. And guys, do we have to introduce something radically new formula? Actually, no, because everything that we need in these relationships, right, is here, right? We have voltage on the left hand side. We have electric field on the right hand side. So pretty much all players are here already. But of course, they are arranged in the wrong, sort of not in the correct order. So what do we have to do with this? We just needed to turn it inside out, this equation. And basically, what is inside out for an integral form of this formula? It's a differential form, right? So we just need to take this and somehow extract the electric field from here and write it in terms of the electric potential. So we just need to massage the this bridge which we built, what, 20 minutes ago. Right? And in order to do it, again, let me open exactly the same picture like what we had in our first slide. You remember that, right? So we just move charge Q from initial to the final point, and the whole area is exposed to the electric field, and the correct angle, blah, blah, right, theta, and the component of the electric field, E sub S, along the S direction, right? So now, how to invert this equation? Of course, we need to write it in a differential form. Basic of the calculus, you remember, right? So in a differential form, it will be dV equals integrand electric field dotted with ds and minus, right? Of course, if you integrate this, you will end up with that exactly. So this is differential form. All right, so now, of course, we can write explicitly this dot product. It will be E cosine theta dot ds, right? And the same story, E cosine theta is just a component of the electric field along that arbitrary direction S. So again, I can use that notation E sub S. So it will be E sub S ds. Okay, so now when we have this form, of course, now I can write E sub S in terms of dV. So now let me solve it for E sub S. So it will be E sub S equal to negative rate of change of the electric field, dV over ds. Now, in order to, basically derivation is done almost. Now we just need to say fancy words and write the formulas. Now, no, not fancy, magic words. So since from the very beginning I told you guys and I emphasized this S direction is completely arbitrary. What does it mean? It can be, so this direction can be S, that direction can be S direction, this direction, any direction can be S direction. No restrictions when we derived this. So since this is true, since S can be any direction, so then of course I can align S direction, or I can say that, yeah, let's say I can align S direction along X axis, right? X is also completely can be S, since S is arbitrary direction. So it means that I can write this using X instead of S. So I can write E sub X equals minus dv over dx. Again, since S is arbitrary, so yeah, I can align it along X direction. It's not wrong. Then, of course, using the same words, pronouncing the same words, I can say, since S is an arbitrary direction, I can align it along Y direction. And as a result, I can write the formula which can be used to find the Y to find the Y component of the electric field. E sub Y will be equal minus dV over dy. And again, pronouncing exactly the same, I can write formula for the Z component of the electric field. E sub Z equals minus dV over dz, rate of change of the electric potential, right, with respect to Z. So that's how we can find components of the electric field. And of course, we can write in the form of a vector, because you remember electric field is a vector quantity. So I can write something like this. Electric field vector, it's E sub x times I hat, E sub y times j hat, E sub z times k hat. And of course, strictly speaking, here it shouldn't be, we shouldn't have a straight derivatives. We should have actually partial derivatives. But for some of you, you might not be familiar with partial derivatives. So usually I don't dive into that, because most of the time we're going to have situations where electric field depends only on one variable, x or y or z, right? So not on all of them. Right. But of course, in some high level courses, you will see that here you have to use partial derivatives, not straight derivatives. But anyway, so that's what we're going to use most of the time. We're going to use just this, right? Because we're going to have most of the time one-dimensional situations. Okay, question. Just I want to emphasize on one part. Look, guys, how come that in order to move from the electric field to the electric potential, this bridge, we have one formula. But in order to move in the opposite direction, in order to find electric field from the electric potential, now we need to use three formulas: this, that, and that. How come? Again, feels like a discrimination of in terms of a direction. This case, in this direction, one formula. In this direction, you need to use three formulas. And again, it's understandable from the nature of these quantities. Electric potential is a scalar quantity, right? So one is enough. But electric field, it's a vector quantity, right? So, and of course, you need to find each component separately, because each component of the electric field, they're independent, right? So you need to have one formula to find x component, another formula to find y component, and then of course the other one in order to find z component. Right. So, all right. So that's the bridge in the opposite direction. This. And now, basically, we need to look at more examples. This example, I'm not going to discuss on the whiteboard. We will solve one problem, something similar, in maybe in 10-15 minutes. But first, I just want to talk about this formula, because application of this bridge is even easier than application of the first bridge which we derived in today's class. So let's assume this situation. We have information about the electric potential. You see how electric potential changes with x. Actually, x is in centimeters. Of course, at some point you have to convert it into meters. And so first electric potential is negative, then it's 0, then it's growing to 10 volts, then stays constant, and then it starts going down again to being negative. So based on this information, we need to plot how electric field changes with x, right? So basically, again, you see one-dimensional case, so we just need to use this formula, nothing else. And what is this? It's basically the negative of the slope of the potential graph, the negative of the slope of the graph v versus x, right? So pretty much, what do you have to do? You just need to split this plot into three, right? First region where we have this straight line, then this region where we have again straight dependence, and then this region where we have a nice straight line. And find slopes of this part, that part, and that part. And of course, we have to remember that there is a minus in front of this. So find the value of the slope and don't forget to add minus in front. Again, place for typical mistakes, right? So students forget about adding minus, right? So it means that here slope can be easily found. You see what in the first region, delta v over delta x. So what is delta v? Final value of v, which is what? 10 volts, right? You see final value in the first region, 10 volts. And then minus the initial value. And the initial value is negative 10. So it's a minus 10, right? As a result, you will get 10 minus 10. It's a 10 plus 10, 20. That's what we have here, 20 volts, and divided by the change in the x. In this case, 2 centimeters. Of course, you have to convert it into meters. 0.02 meters. So if you divide it, you will get 1,000. Again, that's the value of the slope, but we have minus in front in the formula. So as a result, the value of the electric field is negative 1,000 volts per meter. Right? You see, this is even easier. Just a really foundation of calculus, right? So then immediately you can say, and of course you can see on the plot, E versus X, you see, minus 1,000. That's in the first region. The second region, since this is horizontal line, slope is 0. So of course you can tell immediately that the electric field will be 0. So electric field is 0. And then the third region, now, of course, you can see the slope is negative. And of course, the electric field as a result will be positive because that minus in front. But of course, we need to find actually the value of the slope. And in order to find the value of the slope, again, it's a final value minus initial. Final value now is what? In the third region, it's a negative 10 minus initial value 10. So it's a minus 10 minus 10. It will be minus 20. And then divided by change in the x. It will be 8 minus 4. So it will be 4 centimeters. And that's what we have here, right? Minus 20 divided by 0.04. And you will get negative 500 volts per meters. That's the value of the slope. And of course, minus in front gives us plus 500 volts per meters. And that's what we have here. Right. So you see, it's way, way easier. Right. Right. So now there will be a couple of questions for you. And first one, we're not going to poll. All right. I just want you to think by yourself, for yourself, and then I will quickly say a few words. So we have some information about the electric potential. And we need to get some information about electric field. So basically it means that we need to use the bridge which we just built. So you see we have how electric potential changes with x. And we have 2 points, x sub a and x sub b. So based on this information, at which point is the electric potential stronger? And I emphasized absolute value. So we don't care if it's a positive direction, negative direction of the electric field. We just want to know at which point the electric field is stronger. Right? Okay. Think for, I don't know, 10 seconds. It should be enough, right, in order to come up with an answer. And in this case, no polling, right? So Okay, so let me discuss it quickly. So in this case, it's very simple because now we just discussed that in order to get information about the electric field, you just need to know information about the slope. And since we're interested only in the absolute value, this minus doesn't give us, so this minus can be dropped, right? So we just need to see at which point slope is larger. And obviously, by looking at this curve, we can say that slope at point A is larger because curve is growing faster. And of course, slope at point B is smaller. So it means that the electric field is going to be stronger at point A than the value of the electric field at point B, right? And of course, yeah, of course, we can also say some words about direction of the electric field, although it wasn't in the question, right? But we can say that because slope is positive in both cases, point A and point B, so dv over dx is positive, but because of the minus in front, of course, electric field will be negative. What does it mean, negative electric field? Since the electric field is the vector quantity, negative value indicates about its direction. So it means it points in the negative x direction, just right. So we're going to see, we're going to have something like this. Electric field at point A points that way, negative x direction, and at point B, smaller in magnitude, but also points in the negative x direction. Right? But again, the question was only about the strength. Since this vector is longer, you see, of course, it means stronger. Okay, so this is reasonably simple. That's why I didn't want to poll it. And now my all-time favorite question. So what do we have here? We have, you see, some information about the electric potential is given, right? So you see 50 volts, then minus 50 volts. So then plot goes through 0 at x equals 2. And we have an electron. So what if we take an electron and, okay, again, it's, and position it at point x equals 2 and release it. It means that the initial velocity is 0. Initial speed is 0. Release it. And now we need to answer the question, what happens to this electron? Will it move to the, okay, let's option A. Will it just stay at that point? If you just release it and the electron says, it's fine, I'm going to stay here. I'm not going to move anywhere. Point B, will it move to the right at a steady speed with 0 acceleration? Then will it move to the right with acceleration, with increasing speed? Then will it move to the left, negative x direction, with constant speed, 0 acceleration? Or will it move to the left with acceleration, with increasing speed? Okay, the poll again is in the chat. Give it a try. And I explain why I like these questions, because in order to answer it, at least the way I approach it, we need to use a few things which we discussed recently in the past, but you need to arrange them in a proper order in order to come up to the right conclusion. Right? But each of those steps, we're quite familiar with those steps, right? So we should be comfortable with that. But we need to arrange them properly. Okay, let me see your answers. It's a question 2. Yeah. Okay, I see the story. Okay. I see what is happening. I need to make some corrections, adjustments. Let me see if number of answers, number of responses is growing or not. Okay, 21 only out of 27. And it's not growing, it means that 6 students are doing something else. They just entered the class and went to do, oh, 22. Okay, now let me discuss it. Okay, again, let me, okay, one additional response. Great. Okay, let me create a skeleton of this, I don't want to say solution, discussion, skeleton of this discussion. Because again, I find it very useful to have structures. Right? So that when you have the skeleton, then you can just, yeah, skeleton. And then it helps to answer similar questions later. Okay, so now let's start from the very end. We need to get information about direction of motion. And so, direction. How can we get information about the direction of motion? So what is direction of motion? Basically, we need to know what happens with position x, right? X, position of a, in this case of an electron, right? So we just need to know what happens with x in time. But if x growing in time, so it moves in the positive x direction. If x is decreasing, so it means it moves in the negative x direction, right? So, and what is that? What is that information about how x changes in time? It's effectively velocity, right? It's effectively velocity, and basically we just need to play with these kinematic parameters, kinematic quantities. You remember I already told you several times, right, from physics 1. So first level of this kinematic quantities or parameters, it's a position level, right? Distance, displacement, position, right? Position. Then if you dive inside, dive deeper, you will get to the velocity level. If you differentiate, you will get to the velocity level, right? And then below velocity level, if you dive even deeper, you can get to the acceleration level. So now, in order to get information about the direction, basically we need to be on the second level, on the velocity. Once you know information about the velocity, you can tell what's the direction of motion. But what's wrong in this situation? The object, the electron, is released. So the initial velocity is 0, and we need to get information about the direction of motion at the moment of when it is released. And at that moment, velocity is 0. So information about the velocity, we cannot extract information about the direction from the information about the velocity, because velocity is 0. So what can be done if we cannot get information about the direction from the velocity level? We need to dive deeper. Sooner or later, we should be able to find that information, right? So we just need to move to the level of acceleration to get information about, or in an attempt to find information about the direction of motion. But with acceleration, we have to be careful, because it's not as straightforward as with using a velocity to find direction of motion. Because a direction of velocity gives you direction of velocity give us direction of motion immediately. No exceptions, nothing. Object moves this way, it means direction of motion, direction of velocity that way. Velocity this way, it means the direction of motion that way. But with acceleration, we have to be careful. Because you can easily imagine this situation, right? You drive your car, right, I don't know, 60 miles per hour, and you press the brake. What will happen? You will still move in the same direction. So that's your direction of motion. But what's your direction of acceleration? It's that way. Because you're decelerating, you press the brake, so your car is decelerating, but you still move forward. So directions are opposite. Acceleration points that way, but object, okay, car still moves forward. So you see, in this case, direction of acceleration doesn't give us direction of motion all the time. So we have to be careful and pay attention to some details. But in this case, since initial velocity is 0, then direction of acceleration gives us direction of motion immediately. Because imagine yourself, again, if your car is stationary, right, initial velocity is 0, then if you start accelerating that way, of course, that's the direction of your motion. If you start accelerating that way, of course, that will be the direction of motion. No, pretty much in this case, only in this case, direction of acceleration can give us direction of motion. And that's what we have. Our initial velocity is 0, and in this case, direction of acceleration is going to give us direction of motion, right? Okay, so it means that in order to come up with a final answer about this direction, we need to first know information about the acceleration, right? Okay, so now, next step. In order to get information about acceleration, of course, what do we have to know? We need to know something about force. In this case, of course, electric force. And of course, we can use Newton's second law in order to move from this point to that point, right? So now, what do we need to know in order to get information about the electric force? Electric field. And that universal formula for the electric force, F equals QE, can be used to move from this spot, from this point, from the electric field to the electric force. F equals QE. And now the first or the last step, how can we get information about the electric field? That's the bridge which we just established, right? Which we just built 10 minutes ago. Now we know how we can move from the electric potential V to the electric field, and we know the formula E equals as minus dV over dx. So that's basically the skeleton of this discussion. And you see, each of these steps, or pretty much here, we used almost everything that we introduced in this semester. And of course, this is physics 1, right? Newton's second law. And basically, this is what we've been introducing. And now we just need to use them all in the correct order. So now let's start. First, what do we know about the electric potential? dV over dx, it's a slope. Slope of this curve, green curve at point 2. All right, just a second, guys. Okay, now everything, all mics are muted. So we know, you see, by looking at the curve, we can tell that slope of this curve is negative, right? Slope of the curve is negative. dV over dx is negative. right? So dV over dx is negative. And since we have minus in front, so it means that the electric field is going to be positive. Positive electric field, it means it points in the positive x direction because the electric field is the vector quantity. Negative one-dimensional vector, it means points in the negative x direction. Positive one-dimensional vector means it points in the positive x direction. In this case, it means that the electric field is points in the positive x direction. So that's the my arguments and electric field. Here I showed the arrow, right, that way, and I can show it on the graph to the right. Okay, so now we are here. Now next, we need to get information about the electric force, direction of the electric force. So since charge is negative, electron is negative, so in order to get direction of the force, we need to flip direction of the electric field. Electric field points that way, so it means that the electric force is going to point in the opposite direction, negative x direction, right? So now I'm going to use this blue arrow, right? You see, negative x direction. Right, and so now the next step, in order to get information about acceleration, using Newton's second law, and since mass can be only positive, mass can never be negative, so direction of force and direction of acceleration exactly the same all the time. If force that way, it means acceleration that way. If acceleration that way, force that way. So it means that acceleration is also going to be to the left, negative x direction. And of course, we just discussed, since initial velocity is 0, direction of acceleration gives us direction of motion in this case. Right. Right. So that's what I just told you. So that's my way of analyzing this situation. Of course, in a few classes, when we start discussing currents and so on, right, we can come up to this conclusion faster using significantly smaller number of steps. But nevertheless, I like this question because again, we used almost everything that we've introduced in this course. And if you arrange it properly, you can come up with the right conclusion. So that's why it's my all-time favorite question. Have structure, but also at the same time, each step is reasonably simple. We are familiar with these steps. Okay, so that's the, and of course, since this slope dv over dx is not 0, right? So it means that electric field is not 0, electric force is not 0, and as a result, acceleration is not 0. So of course, object moves, okay, electron moves with an acceleration, right? So it's not with the, it is not going to have a steady speed. So the answer is E, of course. Right, so that's how I usually discuss this question. So now next, we still have 15 minutes. It's time to switch to whiteboard and discuss a few problems. So problem 4, chapter 26. So what is given? Information about the electric field is given. Okay, I need to plot it. Okay, I have to do it by hand. Okay, I'll try to do my best. So this is EX units, of course, volts per meters. You remember, instead of newtons per coulombs, we can use also volt per meter. Then here we have X in meters and the plot. Okay, you know what? First I need to put points. So 1, 2, 3. 1, 2, 3. And let's say here we have 100 and 200. And now the plot itself. So first it stays constant up to this point. Then it goes down to x equals 3. So, all right, so that's what is given in terms of about the electric field. And now some information, additional information about the electric potential at a particular point. So what is given? The electric potential at the origin here, V at x equals 0 equals to minus 50 volts. Again, you see the difference over here in this problem and in the conceptual question which we discussed. The value of the potential at a certain point was 0. Now it's negative 50. So we need to we need to be careful with those additional terms which now appear. Okay, so pretty much nothing else to discuss, except for, of course, I need to ask the question, what needs to be found, right? So we need to find the value of the electric potential at x equals 3. So what needs to be found? So find V at x equals 3 meters, right? So we need to use this bridge, how to move from the electric field to the electric potential. And of course, in order to do this, we derive the formula. So delta V equals negative integral from x initial to x final of E sub x dx, right? So general formula first must be written, right, in order to show what you're planning to use. And now we just need to apply it. Again, which point initial, which point should be our initial point, which point should be our final point. In this case, I think it's obvious because some information is given at the origin, so this will be our initial point. X initial is 0 and x final is the point where we want to find the value of the electric potential. Of course, I can change the statement of the problem slightly. I can ask, for example, plot like this can be given, but I can say, let's say the value of the potential at this point is given, and you need to find the value of the potential, for example, at this point. And in this case, of course, you'll have to find the area of the smaller part of this picture. Right? But in this case, this is the initial point, and that is our final point. But of course, on the exam, on the second midterm exam, read the problem carefully. Don't just follow sort of like develop the habit of this is usually initial point and the final point is usually our final point. I mean, the far right point is our final point. No, I can ask, for example, to find the value of the electric field at this point or that point or that point. And I can give the value of this electric field at any point. Right? So just read carefully and don't be trapped by this silly frequency. Right, okay, so now let me write it explicitly now. So it will be delta V equals V at 3. You know what, I can even use the subscript. It doesn't matter, let me use it like this. X equals 3 minus V at x equals 0, right? And equals to that integral minus from 0 to 3 E sub x dx, right? Again, our unknown is here. This is now negative 50, but let me first move this to the right hand side with plus, right? And only then I will start plugging the values. So V at 3 equals to V at 0 and minus, of course, area under the plot minus area over what structure? Okay, let me label for example, this point O, A, B, C, and also let me label this point D. So of course now we need to find area of the whole structure. So area of OA, B, C. Yeah, it's a trapezoid. You can use the formula how to find the area of trapezoid, or you can split it into two parts. Right, rectangle plus a triangle. So let's split into two parts. So it will be v at 3 equals v at 0 is negative 50. So minus 50. Sometimes some students made this, again, unnecessary mistakes because the value of the potential is negative, and this must be moved to that side with plus. They start getting lost in these minuses, right? So as a result, they can end up with wrong sign, right, of this term, right? So just be careful. So minus what? Area of OABD, OABD, and minus area of a triangle, area of BCD, right? Okay, so that can be easily found. Minus 50 volts, minus, so it will be 200 times 2, so it will be negative, okay, let me write, minus 200 volts per meters times 2 meters, right? So that's the area of a rectangle, and area of a triangle, minus 1 over 2. Base is 3 minus 2 meters times the height, which is 200 volts per meters. 200 volts per meters. Okay, so now we just need to add them all up. So 400, 450. This is 1, so this is 100, 450, and minus 100, it's a minus 550. Negative 550 volts